Hello and welcome to this EE228 video where we are going to look at second order differential equations and how to solve them using the zero input and zero state response method. So I want to basically just run through one long example in this video, and that is considering the system described by the second order diff EQ that's y double prime plus 5y prime plus 6y is equal to x. And this problem comes in two parts. Part A is find the zero input response, assuming that the initial conditions on y is 2 and the initial condition on y prime is -5. And part B is find the zero state response given that x of t is 2e to the minus t in positive time. Okay, so these are two sub-problems, each of which has its own differential equation required. However, both of them will make use of the same characteristic. So let's look at that. Again, this would be a double derivative, so I get lambda to the 2, and then there are 5 lambdas because we've got a single derivative times the 5 coefficient and 6 lambda to the zeros. So this is my characteristic equation, and of course this factors into lambda plus 2, lambda plus 3. So the two roots, root 1, we're going to call that -2, and root 2 is -3. So the homogeneous solution will look something like c1 e to the minus 2t plus c2 e to the minus 3t. And so this is something to remember, that an nth order diff EQ will have a homogeneous solution with n terms, right? Second order here, 2 terms, because we have one term in the homogeneous solution for each root, and we'll have 2 roots. Okay, now we're ready to solve part A. We're looking for the zero input response. So that's going to be the second derivative of y zi plus 5 times the first derivative of y zi plus 6 y zi's equals 0. That's the 0 in zero input. And we know that y zi of 0 is 2, and y prime zi of 0 is -5. So since there's no input, there will be no particular solution. So we are just left to have zi, y zi, will be the homogeneous solution. And we've yet to determine what the c1 and c2 are. And we're going to use our initial conditions to do that. So let's go ahead and say that y zi at 0 has to be 2. And we know that it has the form of the homogeneous, so we'll look at c1 e to the 0 plus c2 e to the 0, which tells us that c1 plus c2 has to be 2. And we're also now going to differentiate y zi, so y zi prime, evaluate that at 0, and that has to be -5. So if I differentiate the homogeneous solution, I get -2c1, and I evaluate that at 0, -3c2, evaluated at 0. So this tells me that -2c1 minus 3c2 is equal to -5. If you solve this simultaneous system of equations, you'll get c1 equals 1 and c2 equals 1. So that tells us that y zi of t is 1 e to the minus 2t plus 1 e to the minus 3t, all of which is timed at unit step. And right, we should check this. If we evaluate this at 0, we get y of 0 is 1 plus 1, or 2. And if we differentiate it, we get -2, -3 at 0, and we get -5. So this is a solution that satisfies the initial conditions. So we'll put a box on it. Part B says solve the new differential equation, solve the new problem that has the same diff EQ, y 0 state double prime plus 5 y 0 state prime plus 6y 0 state now equals not 0, but our forcing function, 2e to the minus t u of t. But we also know that we have no initial conditions. So this is y 0 state at 0 is 0, and y 0 state prime at 0 is 0. Alright, so here we're going to have both particular and homogeneous parts. So the particular solution will again look like the forcing function. So let's call it d e to the minus t. And it has to satisfy this inhomogeneous equation. So if I differentiate this twice, I get d e to the minus t minus 5d e to the minus t plus 6d e to the minus t, and that all has to equal 2 e to the minus t. Again, what I've just done is I've plugged in this for each of these after differentiating the appropriate number of times. Okay, so I can match coefficients and cancel out the e to the minus t. And this is again evidence as to why the particular had the particular form it did. If I had e to the any other exponent, once I differentiated, I would still have e to that exponent, but I have no other exponents on the right-hand side. So the particular needs to only have e to the minus t's, because when you differentiate it, you'll just get linear combinations of e to the minus t's. So here I get 5 minus 5 plus 6, so that's 2d equals 2, better known as d equals 1. So the particular solution for this differential equation is just e to the minus t. So now let's go back and see how we can meet our initial conditions. So it's confusing to some people that we have to meet initial conditions if we're talking about the zero state response. But what's peculiar is that we have to meet the zero initial conditions, right? If we just had this was our solution, if you evaluate this at 0, you get 1, right? And that is not what we're saying here. We're saying our initial conditions are 0. So we need to say y0 state at 0 will comprise y particular at 0 and the homogeneous solution at 0. So this is take what we just solved for, evaluate it at 0, e to the 0, and now we're going to have c1, let's call it hat, e to the minus 2 times 0, plus c2 hat, e to the minus 3 times 0. And all of that has to be 0. So if you put this together, you get that c1 plus c2 has to be negative 1. That's one equation but two unknowns, so we got to now take the zero state solution and differentiate it. And that'll be what, minus e to the minus t, that's the derivative of the particular, minus 2c1 hat e to the minus 2t, minus 3c2 hat e to the minus 3t. Now if we evaluate everything here at 0, evaluate it at 0, we get minus 1, minus 2c1, minus 3c2, and that also has to be 0. Oh, I forgot my hat's up here. I'm sorry. Don't go outside without your hat. And I forgot my hat's back here. Hat, hat. So this simplifies to minus 2c1 hat minus 3c2 hat is positive 1. So if you solve this system of equations, you get c1 hat is minus 2 and c2 hat is positive 1. So armed with this information, we can say that the zero state response as a function of time is going to be our e to the minus t minus 2 e to the minus 2t, using this here, plus e to the minus 3t, all of that times u of t. Put a box on that. Alright, so what we have just done is we have taken a second order system and we've decomposed the response due to an input, which was a decaying exponential, right here, and we've decomposed it into its other part, which is due to various initial conditions. Ideally, the output is 2 at time equals 0, and the derivative of the output is minus 5 at time equals 0. Each of those two gives us a response. When we're taking no inputs and only initial conditions, we get the 0 input response. And when we're assuming the initial conditions are 0 and we're only looking at the response due to the forcing function, we get what's called the zero state response. If you were given a problem that was saying, here, take this diffy q, force it with a decaying exponential, and subject it to these initial conditions, you could solve this problem, and then you could solve this problem, and the total solution would be the sum of these two.